The current scientific story of the origin of the universe begins with an explosion, which made space itself expand. About 15 billion years ago, all the matter and energy that today make up the observable universe were concentrated into a space smaller than the head of a pin. The cosmos blew apart in one inconceivably colossal explosion, the Big Bang. And the stuff of the universe, together with the fabric of space itself, began expanding in all directions as they do today. But there is a force at work in the universe that casts a singular shadow over this explanation. Rather than traveling in a uniform manner, that expansion is behaving strangely. Something unusual is happening at the edges, causing matter to travel away from us faster and faster the further away from us it is. Most explosions don't speed up the longer they go on. Scientists believe that dark energy is at play. But what is dark energy? Why are so many scientists sure that it's there? And what does it mean for our understanding of the universe as we know it? I'm Alex McColgan, and you're listening to the Astrum Podcast. Join with me today as we uncover what we know of dark energy and explore some of the ways scientists are trying to understand it. Our universe is much more mysterious than it appears at first glance. Understanding the structure of this universe is something we only really began to do in the last 100 years or so. We had plenty of understanding of stars before that point, but it was yet to be discovered how far away some of those stars actually were. Scientists before then largely believed that the universe was just a single galaxy filled with stars. Although some astronomers began to spot little fuzzy patches, actually galaxies, in the sky and postulated them to be island universes external to our own, nothing was proven until the 1920s when American astronomer Edwin Hubble began studying one such object for himself. While studying what we now call the Andromeda Galaxy in 1923, Hubble realized that one of the stars he was looking at was a Cepheid variable star, a type of star that blinks brighter and dimmer over the course of weeks. Importantly, it had been proven that these stars' periods were linked to their luminosity, so by measuring how regularly the star brightened and dimmed, Hubble could calculate how bright the star should have been. By comparing that to how bright it actually was, he could mathematically calculate how far away it was. Sort of like how knowing that a candle that's further away from you is dimmer than one that's close by. Suddenly, he had a ruler with which he could measure the universe. And what he found surprised him. The star he was examining was so far away, it had to exist outside of our galaxy. This opened up our understanding. But it wasn't long before another surprise arrived. Hubble noticed another strange fact. He was able to see an expanding universe. It felt like an affront, a universe almost like a mobile, dynamic, organic, and expanding entity. It was an observation so disturbing that even Einstein refused to accept it. The German theoretical physicist had just shaken the structures of the scientific foundation by proposing an unimaginable transformation to our old notions about space and time. And even then, he could not accept that the entire universe was something dynamic and changeable. In fact, he was so convinced that our universe was a static entity, Einstein set out to modify his original equations by adding an extra element to stabilize the mathematics of the universe. This addition was called the cosmological constant. For Einstein, the idea that the universe was expanding was so distasteful that he initially couldn't bring himself to accept it. And yet, time and Edwin Hubble proved his static model wrong, making a cosmological constant unnecessary. There is an effect known as the Doppler effect that says that the wavelength of radiation stretches if its origin is moving away from you and compresses if it's moving towards you. Because Hubble knew what frequencies the light from these galaxies ought to be arriving at, he could calculate their direction of travel using this Doppler effect. And he discovered that all the galaxies in the universe were moving away from us. It wasn't long before scientists realized that if they were moving away from us now, they must have once been a whole lot closer. The theory of the Big Bang was born. But another strange fact troubled scientists, one that the Big Bang couldn't quite account for. It wasn't just that the galaxies were moving away from us, they were accelerating away from us. The further away from us they were, the faster they were moving. And acceleration requires energy. Where was this energy coming from? Nobody seemed to know, but it seemed to permeate everywhere. To fill this gap in their knowledge, scientists came up with the idea of dark energy. Applying general relativity to this expanding model universe and comparing it to the latest observational data, scientists realized that the particles we could see, known as baryonic matter, made up only 5% of the universe. Somewhere out there is a shortfall of 95%. It was the only thing that made sense. Matter was congregating strangely, as if something invisible with gravity was pulling it closer together. Scientists called this substance dark matter and attributed to it 27% of that mysterious 95% shortfall. But matter was also being pushed apart. The remaining 68% of the universe had to be the energy that was responsible for that. Undetectable, invisible, but everywhere. The maths proved it. There are a few different ideas about the nature of this energy. For starters, Einstein's cosmological constant raised its head again, this time with a new application. Einstein originally came up with the idea of such a constant as a way of perfectly counteracting gravity, a push to balance its pull, to ensure the universe neither expanded and contracted. But if you start with a bigger cosmological constant, you'd get a universe that tipped into constantly accelerating away from itself, just like we see in real life. Einstein hypothesized that empty space might not truly be nothing, but that it held energy, and it could and did create more of itself. This creation of space would create more energy, increasing the pushing power as time went on. It's unclear why space would have this property though. It was more a recognition that it seemed to than an explanation. To fill the gap, quantum mechanics stepped up to the plate. Scientists of this school hypothesized that perhaps virtual particles were to blame for this extra energy. Virtual particles are pairs of atoms that simply pop into existence as a quirk of the quantum wave function that exists everywhere. They don't stick around for long, as they meet and cancel each other out again, but in the moment before their annihilation, they could, conceivably, push against things, exerting force. This theory had some experimental evidence to back it up. There is some suggestion that virtual particles do in fact exist, at least in some form. But when scientists tried to work out how much energy such particles could create, if this was happening in the vacuum of space, their answer proved to be too large. And not just by a little, by about 120 zeros. When your answer is too big by 120 zeros, there's likely something wrong with your maths. Indeed, this answer got the dubious accolade as the worst theoretical prediction in the history of physics. The third main idea is that of a varying cosmological constant, so not really a constant at all, but rather an adjusting field, like an electrical field or a gravitational field, that accounted for this repelling force throughout space. This force was called quintessence. And it might be the fifth fundamental force of existence if it really does exist. The problem with this idea, however, is the same as the issue with the cosmological constant. There is no explanation as to why it exists. In short, this is still a very poorly understood field of study. More information would be needed before accurate conclusions can be drawn. Spotting something invisible is naturally hard. But studying dark energy through its impact on the universe around us is already underway. Different observatories are attempting this in different ways. BINGO, the Baryon Acoustic Oscillations from the Integrated Neural Gas Observations Telescope in Sao Paulo, Brazil, is a land-based radio telescope that intends to monitor the radiation given off by hydrogen atoms in the dark patches of space between galaxies, to see if there are any unusual distributions of matter that might point to the influence of dark energy. A curious fact about the universe is that matter clusters in waves. It is statistically more likely that there is a distance of around 500 million light-years between any two galaxies than any other number. It's thought that this is to do with ripples in the early universe right after the Big Bang that have coalesced into more solid forms of matter as the universe cooled, locking those ripples into place. Seeing the gaps between such ripples, even in the darkest corners of space, could be very instructive. However, if you really want to spot dark energy's hand over time and space, you need to go big. And it's for that purpose that ESA has just launched the Euclid Space Telescope. Euclid is a wide-angle telescope with a 600 megapixel camera designed to capture visible light and infrared radiation from over a third of the sky. Euclid's mission is to survey this massive patch of sky with a level of detail and sharpness that's 4 times greater than previously achieved by ground-based telescopes. It wants to map everything, going back 10 billion years. The hope is that in so doing, it'll be possible to create a 3D map of the influence of dark energy, with the capacity to see how dark energy's influence has changed or remained constant over all that time. Euclid will also look at individual stars too, but its main objective is sheer volume. This way, the pattern of dark energy will hopefully emerge. Euclid launched on the 1st of July 2023 and has since arrived in its designated L2 Lagrange point. It has already started taking its first images, although these photos of starscapes and galaxies are only tests and do not represent the levels of fidelity Euclid will be able to manage once it has finished its tuning. Once the calibration process is complete, however, it will begin its 6-year mission to map out our stars and hopefully answer important questions like what is the nature of dark energy and whether our understanding of the laws of gravity is really complete. So, fingers crossed that this mission can shed some light on the mystery that is dark energy. For now though, this enigmatic force remains a mystery. It's only because of the universe's expansion that we are aware of it at all. It is otherwise undetectable. But as it makes up over 60% of all that exists in the universe, it must be around us all right now. It pushes on us, just as it pushes on every other galaxy. And slowly but surely, it forces all things apart. Perhaps one day, thanks to dark energy, the only galaxy we will be able to see is our own. All others will have been pushed out past the limits of detectable light, and then there truly will be only a single galaxy in the universe, at least as far as we can see. One day, we may wonder where all the other galaxies have gone. Perhaps we will question if they ever existed at all. Whether the universe eternally expands or whether at some point dark energy will run out, we don't know. But at that point, there would be nothing but gravity, leading to everything compressing back in with a big crunch. What is dark energy? For now, only time and possibly a space telescope called Euclid may tell. Well, that's all we have time for today. I hope you've enjoyed listening to this podcast on dark energy and the Euclid mission. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.